Now we're ready to discuss the closed loop operation of the boost converter. The main problem here is that the duty cycle that we just calculated, which was 83.81%, cannot be tightly controlled in an open loop fashion. And that's because of a lot of disturbances in our system. Let's say there is load current variation, input voltage variation, especially in our battery operated case. And also we have component variation, temperature variation. So even if we um, adjust the duty cycle to be that exact value for the beginning of the operation of the converter, over the time and all of this variation is gonna change and we won't have the accuracy on the output side. So the solution to this problem is a feedback system where we sense the output voltage with a sensor, and this can be simply a resistor divider. And then we compare this sensed output with a known reference voltage to generate an error signal. Then this error signal is going through a compensator, and the purpose of that is making sure that the loop is stable and has enough bandwidth and phase margin for our requirements to meet our design specifications. So the output of a compensator is an analog voltage, but we need to generate this duty cycle. We know that we need a PWM signal for our switches inside the switching converter. So a pulse width modulator is a block that takes this analog control voltage and generates a PWM signal for us, and we will see how shortly. So in general, we can write the output voltage as a function of input voltage, load current, and duty cycle. But only the duty cycle is our control input to the switching converter, and we take input voltage variation and load current variation as disturbances. So our goal is to fully understand the relationship or the transfer function from this control input to our output, and also to maximize rejection of these disturbances to the output. So before calculating this transfer function, let's look at the duty cycle generation one more time. So the circuit, the PWM modulator, is a comparator that takes a sawtooth waveform with a fixed amplitude and compares it with the control voltage. So you can see that this here we have a sawtooth waveform and the control voltage crosses this sawtooth. And depending on this intersection point at the output of comparator, we get different duty cycles. So this is how our PWM waveform is generated. Turns out that this whole block, in terms of AC response, is an attenuator, and the attenuation factor is 1 over the amplitude voltage of the sawtooth waveform. So it doesn't have any dynamic response. It's basically just a gain or an attenuation. So now let's have a qualitative look at our boost in converter case again. So we're interested to see if I start with a duty cycle of D, let's say in steady state, and then suddenly disturb it with a step-in duty cycle which has an amplitude of small d because it's a small signal variation, how my output voltage is affected. So when our duty cycle was D, the output voltage had some value. When we step it up, we expect to see eventually a rise in the output voltage, and that's because because we know that as we increase the duty cycle, our DC gain increases and the output voltage increases. But the main question here is that how is the transient from the lower value of the output voltage to this higher? Do we have this overshoot, undershoot, underdamped, overdamped response? So we can find out this behavior by calculating the transfer function from duty cycle to the output voltage. And for calculating this transfer function in Laplace domain, we assume that all other disturbances are zero. So it's basically like a superposition. We zero all other variables and just look at our input to output transfer function. But before going through the equations to find this transfer function, let's see if we can make guesses on this intuitively. So the first guess is that we know that the DC relationship between VO and D is 1 over 1 minus D. So that means the low frequency component of this transfer function is the derivative of 1 over 1 minus D, which is 1 over D prime. So that derivative is 1 over D prime squared. The other qualitative observation is that this transfer function is going to have a right half plane 0. So in the numerator, we will expect to see a 0. And that's because the inductor current or the inductor is connected to the input side. If I increase the duty cycle, initially the on time expands and the inductor current is connected to the input side for a longer period. This means I charge the inductor current for a longer time, and the discharge of the output capacitor also takes a longer time. Since the discharge of the output is longer, it means that the output voltage initially goes low, and eventually the inductor current charges up to a higher value, and that compensates for the initial dip in the output voltage. So this behavior, when we expect a variable to go up, but in the beginning of the transition it dips, this means an existence of a right half plane 0 in our transfer function. How about the denominator of this transfer function? Because we're looking at the second order system with L and C, I expect to see a second order transfer function. So in summary, we can say that it's going to be a 1 over D prime squared low frequency gain times a right half plane 0 divided by a second order term in denominator. Now let's do the algebra.